just double check that it's working. Okay. All right, so today we're going to continue talking about smooth particle hydrodynamics fluids. And I was playing with the code that we left off from last time, and I got some really neat bad behavior that was making me, I was just laughing because it was just very strange behavior. We're going to take a look at that first, and then we're going to try and fix it. Okay, so today we're basically talking about emergent behavior of a broken SPH system, and then continue implementing SPH. Now, does anybody remember where we left off last time as far as implementation goes for SPH? Yeah, we were talking about the density, and so let me go over. Let's close. Let me open up our week. I want to say week 8 kind of has our main things. So does week 11. Okay. And let me go to the equation we're actually trying to solve. Here we go. This is the equation. So I'm going to put this up on the board just for reference. So we have du dt okay, this is a vector. So we have a vector field that we're trying to differentiate with respect to time. What's the differentiation of velocity with respect to time? Acceleration. So we're trying to compute acceleration. What do you think we're going to use this acceleration for?
What are we going to use it for?
Yeah, what are we going to use the acceleration for?
I mean, to move, control particle position.
Yeah, that's our force. That's like our acceleration operator for the particle. Okay. All right. So then we take what's this operator called? Viscosity. What's that?
That term or the
This. What's that called?
oh,
Not the gradient.
no.
Huh?
Oh.
This is the Laplacian. This right here is the Laplacian.
Yeah.
Okay.
Upside down.
Yeah. Yeah. If you're trying to get access to those symbols, this is the LaTeX/Nabla. Okay. But we say Del because that's what it is. Del Taco. That's right.
that was a joke. My calculus.
I do like it.
That's why I remember the name.
Yes. Okay. That's fine. All right. Yeah. So we have yeah. So if we have a vector field, that is that's the gradient. Okay. And that's the Laplacian. Does anybody remember what divergence looks like?
Is it Nabla dot?
Yeah, del dot. Okay, so if you have that, that's going to be the divergence. Now, what is the gradient? If we're just talking about regular old, just plain old calculus, you're talking to somebody who knows calculus 1, what is the gradient basically like? Derivative. Okay, and divergence is basically the what? Integral. Okay, so sometimes useful to think this is kind of like integration. This is kind of like derivatives. Okay, the Laplacian, it's kind of like the Laplacian.
Double.
Well, not really, because this has that dot product in there. This has got, it's a little bit different. Okay. Anyways, we need the divergence there. We're doing the gradient. So we call this the pressure gradient. And what do we call this one?
The viscosity term?
Well, this is the kinematic viscosity. So this is not really the viscosity term, but diffusion. Okay. Now, when we think of diffusion, what do we think that means? Spreading around, right? If you have, diffusion, spreading. Okay. And then this is our
Outside.
external forces. We put gravity here just because we're probably doing gravity, right? Okay, so, and then this is acceleration. All right, so we got this equation over here that we're building up on, and I wanted to spend a little bit of time talking about, I think I was updating on week 11, I was updating some stuff that we didn't talk about last time. So this is like week 11, week 12 kind of stuff, week 13 kind of stuff. So for one, we're still going to work on the mass spring damper, the collision stuff. Hopefully we can get through SPH this week and then get through mass spring dampers next week. That's what I'm hoping. Okay. Anybody opposed to having extra in-class sessions for covering these particular topics? Okay. So, because the only issue with if we do hybrid topics for those, then you get 15-20 minutes, right, of talking about that, but then very little time spent on implementation part, which is what I'd like to at least spend some time talking about those.
Will there be like stream of it for those of us that can't make it?
Yeah, I'll stream there. Okay, so the first, so we were talking about the SPH kernel. So we implemented the SPH kernel. That more or less is pretty straightforward. You just implement that as a math function, right? A function inside the. Then we got to calculate density. Now, density was, we talked about. This is pretty simple, right? The mass of particle J times the SPH kernel times x minus xj. So whatever the, I want to say that's particle xi. I could be a little bit wrong on that one. But the idea here is the density. We basically calculate density by saying, hey, what is the distance, kind of like the 3D distance, right, from our particle. So, I mean, but we look over here, this function, the SPH kernel, what does it map? It maps a vector to a scalar, right? So maps a vector to a scalar, and we calculate r as that's the distance. So that's the magnitude of r, right? So we take the magnitude of r, which is the magnitude of x minus xj, and then we divide it by s, and s has to do, that's the radius of that's the radius of the kernel. Okay, so if r is 0, in other words, we're talking about particle I to particle I, what do we expect a function to go to for the kernel? If R is 0, what happens to, first of all, what happens to the R over S term? Because that affects which case we pick. Let me make this bigger. So we're going to pick the first case, right? Yeah, just one, because this term goes to 0. 0 over S is going to be 0. This term is going to be 0 as well. We pick this first case because R over S is going to be 0. So then if we're going from particle I to particle I, there's no distance between the two. So technically we always map the mass, right? What does it tell us about this one, the mass of particle I to particle I? What happens to density?
So if we're saying the kernel is always 1.
Mm-hmm.
Just the sum of the mass.
That's just the mass of that particle. So if we're going particle I to particle I, then the mass is the mass of the whole particle, right? So we always include the total mass of the originating particle, okay? Just for reference, I'll put this picture over here, right? This is particle I, and these other particles, we'll put this as the radius of the kernel. So this particle, I'll call this one K, and we'll call one of these particles J. Okay, so particle K, theoretically, what should happen to particle K? This is the outer radius of the kernel. Looking at the kernel itself, what happens when you're on that very outside edge? Nothing. You don't get no mass from that kernel, right? For particle K, we don't get anything. And particle J is going to be what value? Some value between 0 and is it 2? Let's just say that R and S equals the same thing. Or actually that R is 2 times S. Right? Because we have this case, right? R is 2 over S. Then we have, that's R over S is 2. 2 minus 2, 0, okay? Well, minimally speaking, if it's between, right, I guess this is a S over, this is, the outside one is 2R, this is R. Okay, so J is outside, so it's going to be some value between 0 and 1/4, right? Okay, and if we had another particle inside here, then that should be between 1/4 and 1, right?
So it's how much introduce the density of these.
Right. So nearby, so if you have a lot of particles nearby this object, then we're going to get a lot of, the density would be really high in that area until eventually it fades out. In other words, we want something that kind of looks like this. We want something that kind of looks like this, where by the time you get to here, which is R equal S, then by the time you get out here, then you're just quickly letting it go. Okay, that's, and it basically is like a logistic kind of function in the sense of, no, not the logistic function, sorry. Wrong idea. It's like the Gaussian bell curve. That's basically what we're trying to do. Okay, so this is a so the SPH kernel here is a value that maps a vector to a scalar. Okay, so what we're going to do here is we want, in order to get the density of particle I, we need to go around and measure the smoothing kernel times the mass of that particle. That's how we're going to come up with the density. Okay, then we're going to calculate pressure.
Just to clarify, it's the smoothing kernel times the mass of the particles.
Right, but you can do its own part of it. You need to do itself as well, because if you're summing up the density and you don't include yourself, then you're ignoring your own mass. Okay, you're basically, like I said, you're just trying to calculate what's the density of everything within this kind of like sphere around it. Okay, so now then I threw out this equation last time, like, hey, P equals K times rho I minus rho naught, and I said K is some, what kind of value did we say K was going to be? Stiffness, right? But I didn't really define it, right? So, so this is where one of those things. Okay, it's like, all right, I don't like having parameters. I don't know what the heck they are. Okay, so I looked this up, and this is kind of based off the Cole equation, and it's kind of fun to look this stuff up, because I'm like, well, what's the Cole equation? I don't want the Cole equation. The Cole equation. Let's look up density. I think I closed down all the other. Maybe I need to look up smooth particle hydrodynamics. Okay, so this is another picture of what we're drawing over here, right? This is the smoothing kernel. Okay, you'll see that in the middle, that's where you get most of it, and then it fades off. Okay, so blah blah blah. Over here, they're talking about hydrodynamics. So when we're modeling things, okay. Here's another picture of the. This is something interesting too. You know, what happens if you have a boundary? You know, you have to do kind of some figuration. You have to do some. We're not doing it in this class, but this is one more complexity. What do you do with particles on the edge of the border? Okay.
Border being the surface.
Yeah, like think of swimming pool. The walls would be the border. You'd have to, as you got closer and closer to the border, now the wall is part of the, you know, part of the issue. Okay, and that's applying a force with the, you know, the particles are applying a force to the wall. Therefore, the wall itself is applying a force to the particles. Okay, so anyways, the pressure equals this constant K times rho I minus rho naught. Okay, so I'm like, okay, well, what's K? So we said it was a stiffness constant, and so I was looking up over here, and I found this one relationship over here where they related the speed of sound times rho minus rho naught. So I was kind of curious, well, where does that come from? Is it like a stiffness constant, or is this the speed of sound squared? Okay, so that's interesting, right? Because you're like, how do you figure that out, and what is that supposed to be? Because remember I told you when you're experimenting with this, with particle, with the fluid stuff, what kind of values should you be throwing into these equations? Realistic values. What happens if you don't throw realistic values in your equations? You start optimizing a problem that's wrong to begin with. Okay. In other words, you're like, well, that doesn't look like a fluid, and you start tweaking parameters until it's like, that looks like a fluid now, and then it doesn't. But then you're like struggling with it to get get it to act right. You're like, well, I want it to act like lava. And you're like, well, okay, how do I set this up so that it looks like lava? And maybe you don't ever quite get there. So, however, you know that the stuff works in real life because we can see it, right? We can see lava or foam or any number of things. Okay, so c squared. So I was like, okay, well, how is that related? So there was the Cole equation here. This is what I was looking for. And because this is the equation that they mention in the book where you have rho naught times c squared over gamma, and then you have rho over rho naught to the gamma minus 1 plus the initial pressure. Okay, so rho naught is the reference density, c is the speed of sound. So I was looking at the Cole equation, and I was like, oh, okay, that doesn't tell me anything. That's B. That's like, I figured that's kind of where they were getting the, you know, you can kind of rearrange this equation so you get K times rho minus rho naught, right? Because if you just multiply, so, because they said, you know, a lot of times you said gamma equal to 1, so then that's just rho minus rho naught minus 1. So then if you make B, you know, some product of rho naught times some constant, then you can get rho minus rho naught. Okay, so doesn't really answer my question. You know, we're doing like, it's like finding Where's Waldo in a bunch of equations. You're like jumping from the place to place. We have some clues, or maybe we're like Sherlock Holmes trying to use deductive reasoning. Where does this stuff come from? So Cole equation's kind of like, okay, that's interesting. That's not. We have this index here, adiabatic index. I don't want to go there. I feel like it's getting further from where I want to be. But so I go back to over here. So it's obvious in this equation that rho naught times c squared over gamma, that is that's the B in Cole's equation, right? And that makes sense, right? Because if we multiply this out, then we're going to get rho minus rho naught. So c squared, but we have this, you know, if we set gamma equal to 1, then we can kind of get rid of the gamma. Okay, so over here, they were talking about Mach numbers and so on, but basically we have the speed of sound. And so another way of thinking about this constant c squared is that it's not, there is an equation called the bulk modulus. And so the value of c is equal to the square root of the bulk modulus over the density of the material. So I'm like, oh, okay, we're getting somewhere here. So I went ahead and I don't know if I can just, I don't think they mentioned the bulk modulus here. I'm just going to guess that this is what it is. Yes, okay. Bulk modulus, it's a substance, is a measure of how resistant to compression that substance is. I was like, oh, stiffness constant. This makes total sense right here, okay? So this is where it's kind of confusing because we're using K over here, and the book had K times, it's a different K, but, you know, we're kind of like, obviously they read a different book. Because a lot of times you open a different book and they use slightly different. The form looks the same, but they use maybe slightly different values. So over here, they said, okay, for gases, the bulk modulus is gamma times P. That's the pressure. But we're not dealing with ideal gases. We want actual things like rubber or something like that. So over here is where we get the, I guess, gamma is the heat capacity ratio, and that's adiabatic index. So there's a few different things there. But you have this formula called the Newton-Laplace formula, C equal K over rho, and that's where we get this. So they said in solids, Ks and Kt they're basically the same value. So I was like, well, we're trying to do something that's not a gas, okay? But we might want to do things that are blending between solids and liquid and just complete, you know, so water, right? Water is kind of like our, I guess we could do gas as well. But I was like, okay, let's find out what some realistic values are for this. So we have like rubber is 1.5, glass is 35 to 55, steel 160, diamond 443. These numbers get really, really high. So I'm just trying to find realistic values because I want to put a slider in there that allows me to control this, right? So I basically decided that, well, rubber is already pretty hard, so 2 or 3 is a good maximum value, right? And I was looking over here at like water and air. Now you notice that this is GPa, so like gigapascals. That's so billions, or we're talking about a number that's like a billion. So we have a number. So this basically, rubber is like 1.5 to 2 billion gigapascals. Over here they have some other approximate bulk modulus for other substances. So water is 2.2 GPa. Methanol, I don't know why I would want to simulate that, but you'll notice that it's going down, right? We might want to do that, but 142 kilopascals for air, 101 kilopascals for air. So so when we look at this scale for this Ks, it's clear to me that we want probably a max of 3 GPa, kind of at the higher end. And since air is kind of a good bottom number to go with, right? That's 142 kilopascals, so that's 0.000001. Oh, that's mega 142. Okay. So if we go just air like constant, okay, so using this as like 0.0001 is probably a good lower number for that. So basically, we don't want to go much lower than that because air is already pretty. If you're simulating air, it's not that interesting. I figured that's a good bottom. Like clearly, we're not interested in solid helium. I mean, maybe you are, but so here's what happens. So then you have to say, okay, I got my bulk value here, and so now I want to divide it by rho, and rho. Then you have to talk about density. Okay, so I'm like, okay, well, let's find out what are realistic values for density. So with density, here's a nice little table here. So we got helium 0.179 kilograms per meters cubed. Air 1.2. I don't have my calculator on me, but if we plug in this value, right, square root of if we plug in this value of K, which is 0.001, that's gigapascals. So actually, this let's throw it in as just regular pascal. So 100,000 or 101,000 divided by what's 1.2 for air, and then we take the square root of that. We get 290 kilometers meters per second. 290 meters per second. Does that sound about right for the velocity of sound? $343 meters per second, right? So if we use I know for sure if we use the 142 divided by 1.2, and then we take the square root of that, 343. Okay, so that's where we are. Okay, so that's nice. That math checks out. So I kind of like that idea that we can use realistic values for. We can get realistic values for just by looking at the bulk modulus and the density. That's kind of neat. We can kind of make our own materials if we wanted to experiment with that. So here's where this comes into play. We go back here, right, and we say that C equals the root of Ks over rho, and K is the stiffness constant equal to C squared. What do you think our pressure over here, this P value is going to equal? Is K going to be a number between 0 and 1? What do you think? Because when I think like a stiffness constant, I think, oh, is that like 0 to 1? What's that?
Normally think dampening with it. So.
Yeah, damping. But sometimes we like to measure things. Like we like to give the artist the control of like, just give me 0 to 1. Like 100% is like all the way stiff, and 0 is not stiff at all, right? We like numbers like that. But is this K value? What do we think the range of values is for K?
Well, I mean, KS goes up to 3. And like, you have the formula.
Yeah, yeah.
So, I mean, the real question is what's the range of the rho values looks like. So, and that's, I can vary a lot. So, I don't know. It seems like it's got a pretty decent possible range on it. At the very least, it goes up to 3.
Well, not really. It didn't go up to 3. We're talking gigapascals here.
Yeah.
Let's do the calculator. No, it's not like a small number. It's a really big number. It's a really huge number. We type in, there's thousands, millions, billions. And we divide that by, I don't know, let's go with rubber or water. Okay, so it's 2.2, right? That's or actually we need to look that up, I guess. So the density of something like cork, 240. Okay, that's. So we're talking a number that KS value is like 12.5 million.
For some nonlinear sliders.
Okay. Well, we're gonna use a slider to go from like something small like 0.1 or so to like 3. You know, we'll use something reasonable. But let's think about this more detailed. Okay. This rho naught is the reference density of the entire material. That's more or less what is the density of this, like, say we're simulating 1 cubic meter of water. Okay, that reference density is basically how much water is inside 1 cubic meter, right? So if our K value is this ridiculously huge number, like we just saw, like 12.5 million, what do you think that the difference between Pi and rho naught is supposed to be? We're talking pressure, which is a measure of force. What do you think it tells us about the range of numbers we should be expecting from rho I? They should be very tiny. In other words, the density is almost constant. It's almost the same thing as the overall reference density. So we're talking really tiny fluctuations in density cause big changes in pressure, right? Big changes in pressure. I guess that makes sense, right? You push. That's why hydraulics work the way they do, right? Because you just apply pressure and it can apply a huge force to the other side. Okay, so I say that because the initial time I'm going around, I'm like, this is. The particles are acting very strangely. So anyways, so the first thing I was doing is, okay, let's go ahead and figure out, let's calculate the pressure for each of the particles. That's where I'm at. I'm at this step. This is where we are here right now. We'd like to get to diffusion, but for right now we're taking, we want to look at the pressure. So we have 1 over the density times the pressure gradient. Now, we know how to calculate rho I. That's where we just sum up the mass of all the particles times our SPH kernel. Okay, so we know how to get this value, rho I. Now, pressure I, the way we're going to calculate that is we're going to take rho I minus the reference density. So that's actually not so bad, right? It's just a simple multiply the square of the speed of sound, which we can calculate based off, so we can control Ks and rho and figure out what it ought to be. In order to calculate the pressure, and we are expecting that the K values are going to be really, really big, and we should expect that the change in density compared to the reference density should be very, very small, That way we get reasonable values for pressure. Okay, and that's so that's that first step. And then the next step is to figure out the pressure gradient. Now, can anybody tell me what the gradient of a scalar field is going to be? Because that's the next step. We need to figure out what's the gradient of a scalar field. It's a vector. Okay? So, that SPH kernel over here, right, WR, turns a vector into a scalar. Okay, so we cannot use that. So that means that when we look at the other gradients, we want to kind of be in tune to this. That there's the kernel. This is when you look at this. Okay, we're looking at this and we're like, well, how does this turn into a vector? Because that's what I was staring at. I was looking at this and like, how does this turn into a vector? dWdr. So so what we have to do here then is the W is going to be our X, Y, and Z, right? So if we go down here to, nope, that's the. So we're going to take. So you notice over here the pressure gradient. We're taking the gradient of W. Okay, so when we take the gradient of W, what does that mean? That's going to be a vector, sure, but what does that mean we have to do with this difference of x minus xj? We have to differentiate with respect to no, not r. We got to take the derivative with respect to x, and then with respect to y, and then with respect to z. Okay, that's what we're doing with the. That's what we're doing with the SPH kernel. Okay, so it's one of those cases where you're looking in the book, or you're studying this algorithm out, and you're like, how come this looks a little bit crazy? Okay, so now one of the things the book notes is that given an appropriate kernel function W in closed form, which we have, gradient W and the Laplacian of W can also be computed in closed form so that no numerical differentiation needs to be done. So that's kind of good, okay? Since the kernel is radially symmetric, i.e. it is a function only of distance from its center, we need only compute its first and second derivatives with respect to R to determine its gradient in Laplacian. Okay, so what I believe that's trying to say is that the derivative with respect to, I think what it means, the derivative with respect to x, y, and z is all the same because it's radial. It's not going to, I think, yeah. So that's the hypothesis, right? So now we got to test it. Okay, so just to keep this interesting, I wanted to show you what's happening to the. So if I hit reset, I think this is cool. Okay, so I start, the particles have no velocity. So technically, the only thing we can do is crash the program. Okay, that wasn't what I expected. Reset. And I need to zoom this out a little bit. Okay, so hopefully this doesn't. You'll notice that, remember, we were coloring the particles based off the pressure or density. I can't remember if it's density or pressure. So the idea is that it'll be blue if there's very little density, and it should be pink if it's high density. So that's kind of how we're visualizing this. Apologize if you're colorblind. I guess that's could make a difference, but I thought it was interesting. I'm going to change the support radius. So I want to max this out. I think that's what I have to do at first.
That's better than 20 seconds a frame.
Yeah, it's doing. Let's see if it's going to cooperate with me.
It seems to be doing the grouping thing. Put it up that way.
Well, if I set it all the way up. What's that? I think it has to do with that the support radius is so big that the no, it's going to do some even crazier stuff.
That's cool.
If I'm correct, this is going to turn into a circle. This is going slow because I'm trying to encode video at the same time. Now, I believe this pattern what'll happen with this one is that they're going to form little tiny groups off on their own.
Collision forces.
What's that?
The collisions and forces.
The collisions, oh yeah, the collisions add something, but it's not. This will help. We turn the drag all the way up. This slows the particles down. That drag has been very useful for getting them to like not do what they want. Perfect. Okay. Yeah, I forgot to turn the drag up. Yeah, so depending on the radius size, it starts. Yeah, they start forming these little grids, and I can control the size based off of the support radius. It's very strange. I'm calling it emergent behavior of a broken SPH system. Okay, so then there was this this factor. So then if I turn this down, like less than the density, like less than 1, then they're gonna like. Let me open this up.
Just discovered the electron. Good job.
Oh, Alex, I think you with this book is being done.
Can't remember. Okay, let me throw them apart. Turn the density up.
Huh. Clearly simulating something. I'm not quite sure what.
So the screensaver.
Do people actually still like get fancy screensavers and put them on their computers?
Like wallpaper.
I feel like somebody, yeah, at some point in time, made screensavers sound like a security risk, and then they disappeared.
That vaguely sounds familiar.
But
We don't really need
I think the monitors are more resilient now. Although for a time there, yeah, you had the burn-in issue. Okay, I have this circle.
Your desktop wallpaper now is supposed to screensaver.
Yeah. So if I set the density, okay, so this one, there's like a few particles that hang out on their own and the rest go into circles. Although occasionally you will see a few of these like merge into this mass.
They're all continuously migrating away from the center. Like there's something weird going on that makes them not want to be in the middle. Like even that mass is like, go to the
Well, it's just kind of weird because this one over here, it forms this little tiny like semis. It's strange.
Where's the center point of that? It's not centered on that mass, is it?
Yeah, a lot of these particles are interacting with each other, but for some reason these ones are like really not attracted to the center.
Well, I was just wondering if they were being repulsed by it, or that structure was being defined by it.
Kind of. Let me set this down. If I set the support radius small, then I believe this causes it to group up again into the grid. And then if I turn the density up, then they're going to go into a circle. Or they have to go really down. Let's see if this is... Oh, reset. They normally like merge together and then maybe I have to do something with the KS.
The collision system is having problems inside that ball.
Not necessarily. Where's the? I should have wrote this down.
And it might just be the visuals though.
Turn off the. Trying to remember the exact pattern for them to like group up in a circle. I think it's this one. And they form like a nice circle. It's not like this mass over here. It's going to turn into a... There we go.
Not entirely sure that should have happened.
That's why I say emergent behavior of a broken SPH simulation. So I have I'm going to keep this because it's cool. I can manipulate it and get those patterns. I can get them to group together, a little like a grid, or I can make a circle. Let's see if I... And I think it more or less happens if it's greater, if density is greater than 1. And then if I turn the density down, so you basically you have a circle here. And if I turn the density down to less than 1, then it's going to like enfold in on itself, and you're going to get all these particles down here are going to form this little half circle.
Thank you, emergent behavior. You're very entertaining.
So it's very, very strange. Sometimes you get a little bit of a separation gap over here, but you have this like mass here. I'm like, how do these ones decide that they're not going to like be part of the party, right? So yeah, it's very cool. I'm keeping this because I want to study it more and find out why does this happen. I'm still unraveling this this mystery, and all I've really done is this part over here where the accelerations are purely defined by the calculated pressure. So let's see if we can unravel this, because I'd like to figure out what's going on. Okay, so let me go back to the index. Hopefully that was interesting side trail. So let's go to, we need to fix the parameters on here so that we don't get annoyed. Okay, so we're well, first let's go to the simulation. A good way to get some of your CPU cycles back is to minimize the browser that's doing the JavaScript, because whatever the current tab is open, that's the one that's actively doing a simulation, and if the window thinks it's hidden, then it stops it. So either switch tabs or something like that. Okay, so over here I want to set my objects to set default objects to 50. I'm going to set the default mass to 25. Don't add any initial probabilities, and let's create some drag on the particles so they kind of slow down a little bit. Eventually we want to turn off the drag, but the reason for doing that is simply to they start moving really quickly. So okay, and the collisions are turned off because technically we're thinking of them like infinitesimally small particles of a certain mass. Of theoretically it shouldn't do anything. Okay, so yeah, I'm trying to figure out why are these grouping. So let's go take a look at the let's minimize that, and let's go take a look at what we did to create this. So SPH basically calls initialize, density, pressure. We're going to work on some diffusion and then apply the forces. Okay, so if we look at the applied forces, we're using this leapfrog technique where right now we're starting with the pressure gradient. So the pressure gradient is this value. And if we go half a time step, so we accumulate the acceleration half the time step with half the time step, and for the velocity, so we say, okay, take half of the acceleration and apply that to the velocity. Then we apply the velocity for the entire time step, and then we apply the other half of the acceleration to the velocity.
But is pressure pointing the right way? Because like I'm seeing an attractive force, so I'm used to thinking of like unless there's an outside force implying the pressure, the most pressure forces push you out.
So I might
Like
already be calculating the negative, right? Because addition of a negative number is the same thing as subtraction. Okay, so we just want to make sure that the sign is correct over here.
Well, that's what I'm
Yeah.
wondering. Because like I said, I'm seeing clumping, and like I should be seeing a pseudo diffusion from the
Sure. So we're gonna take a look at that. Okay, and so first initialize density, pressure. So let's look at those functions. Forces, it's pretty easy to look at the forces. dt, we decided we were going to do a fixed time step of 0.01 every time we ran this. Okay, so let's just see if this more or less matches what we're doing. Okay, so Pmin, Pmax, I was going to measure pressure so we could basically just see what the forces are looking like. Okay, so initially I set the density equal to 0. And then I also have the matrix of the weights. So when we call density, it's the next function. So we go through all objects I, so O1, all objects O2. We need to include ourselves, so I got rid of this if IE equals J. So first we calculate the support vector, the SPH kernel, so that's SPHW, with the radius, the support radius we've given it. And then this D was just so we could kind of see what that looks like. So we're not using D for right now, but so don't confuse that with density. So then I have a matrix that I just figure might as well calculate all of the respective SPH kernel weights, and this is for W, DW, and DDW because we're going to use those for the Laplacian and for the gradient. Okay, and then I calculate the density. So we just said it's O2m times W. So that's if we look over here, scroll down here.
Are you starting the interlude at?
There's this. So mass times W. That's basically, we sum that up. The inner loop is not starting at I. We're every single pair. Now I guess maybe we don't want to do that
Because you're setting both of them anyway, right? O1 and O2, you're setting the weight there. So I think you're doing it twice.
It might be happening. Well, yeah, it is a question mark. So here's if we start at J equals I, then what will happen is that I think that I only happens one time. And then J to I when they're the same.
Right, but
the problem is that if you particle J's density has to include I guess the only way that if J equals I, the only time that ever happens is that it only happens one time.
I think it's making sense.
Yeah. But initially I had it, let's start off at I plus 1 because that's the way you normally think of like nesting two loops together. But in this case, we want to go the other way around. In other words, in order to update particle J down here, because we're doing O1.density, but we need to make sure that we don't accidentally start if we start at object 5, then we're ignoring objects 0, 1, 2, 3, and 4, and that's incorrect. So we need to make sure that we go 0, 1, 2, 3, 4, and then include our own.
I guess what I'm thinking is you start on 0 in the first, and they're the same. You're iterating through the same list of objects. So you're going to set the weight according to each other of 0 and something in the middle, and then when you get here, it's the exact same thing. Does that make sense what I'm doing?
Yeah, I see what you're saying. I don't think that's correct. Let's say we had 3 objects.
Okay.
So 0, 1, 2, and so we have the first loop I with the second loop j. So the first time we go, we're going to do 0, 0,
right.
Then 0, 1, then 0, 2,
right.
Then we're going to do 1, 0, 1, 1, 1, 2, and then 2, 0, 2, 1, 2, 2.
Right.
So we never do 0, 0 twice. We never do 1, 1 twice. Okay. We never do 2, 2 twice.
Understood, but is not 0, 1, and 1, 0 the exact same thing?
0, 1, and 1, 0.
And 0, 2, and 2, 0.
The reason why they're not the same, that they're the same pair, but if you look at we're only updating density for object 1. So we only update, so in this case, 0, 1, we're updating this density, and 1, 0, we're updating this density.
Gotcha.
Okay.
I was looking up there at the B.
Oh, gotcha.
You're adding the weights to both.
Am I?
0. Yeah, but you said we're not doing anything with the D.
The D is a measure of the. Sorry, yeah. Don't get D confused with density. D was a measure of the kernel. We want to find out how much each particle is being affected by the kernels.
Gotcha.
So that's kind of an older.
So would it be okay?
I could delete it.
Would it be okay though to say below O1 dot density to say O2 dot density plus equals O1 dot mass times weight? Is that not the same thing?
You could do that, but I think just to avoid.
Sure.
We'll optimize that later.
Makes sense. Okay.
Yeah.
I just yes.
Because we're trying to make this match the equations as close as possible. So, so for this case, yeah, it makes sense for us to do M. Yeah, to just update object 1. Okay, there's probably more efficient ways of doing it, but for sake of simplicity, we'll only do it this way. Okay, so then we want to calculate row 0, row naught. Row naught is the from the I think week 11. Let me open up week 11 again. Row naught, we could say, well, we could calculate the overall density by saying what's the density of the material times gravity times height, and that could give us our the pressure for that particle at that point. Okay, so that's what we're doing there. We're calculating the reference density. And then we're doing C2, C squared times the density of O1 minus rho naught. So that's exactly the same, and that's how we get our pressure. And then over here, I'm just capturing the minimum maximum values for the pressure. That way we can color the particle based on what its pressure is. So if it's got 0 pressure, then it'll be blue, straight blue. And if it's maximum pressure that we've seen, then it'll be bright pink. Okay. Okay, so that's how we calculate the density, and that's pretty straightforward. Now pressure, this is where we're calculating the pressure gradient. Okay, so we've calculated P and rho, and so calculate density is not really accurate. Pressure is kind of just how I was implementing it out. So let's just refactor so it's a little more correct. of doing that. Okay, so refractor is named better now. So now we're going to calculate the pressure gradient. So, so now we have dW equals, we already calculated the derivative there already in the previous function. So we're going to need dW, and now we're going to calculate, so what we're doing now, let me go back to week 8. Now we're doing this calculation right here. So if we want to calculate the pressure gradient, we can take the sum of mass J times the pressure for particle I over rho squared, and the pressure for J over for particle J over rho squared for J, times then we have the gradient for W. Okay. Now this is maybe this is where we're getting our problem. In fact, I think this is where we are getting the problem, as Dane mentioned, because we don't have the minus sign in there. So we'll see what happens when we do this. So you'll see this is more or less just we're accumulating. So xi minus xj is just the difference between those two vectors, and then we're multiplying O2 mass. So let's go back over here. So mass of J, so that's object 2, times this is the velocity of J minus the velocity of I over rho I. No, that's diffusion, sorry. There, so we're doing this calculation. This is the next calculation. So mass times this calculation. So you see over here, object 2, so this is technically J times P over rho 1 squared, O2 minus rho 2 squared, times dW. Okay, well, let's see if the minus sign fixes it. It's a blob. Okay. So I guess the idea is that as they get too close to the center, then the pressure increases and drives them out.
That's not just a circle though. Like they're forming sub.
That's pretty cool.
Okay, let's max it out. Let's do 500 particles. This is
It's got like rails and clusters. Yeah, that's really interesting.
The problem is though, is it's not like a physical phenomenon we're trying to analyze. It's a simulation that failed to be a physical phenomenon.
Really new.
Yeah, it's kind of still like there's that circle artifact that's like being created there.
yeah. Well, I mean, I can almost assure you that the circle artifact has to do with the fact that we have a support radius, right? We can affect the fact that it is a circular function. And I bet if it were looking in 3D, it would be a spherical function, right?
Oh, it shouldn't be too hard to set up, right?
Well, technically no, but then it's harder to debug. So we figure if it's not working in 2D, it won't work in 3D, and that's another like kind of keep it simple. So let me throw the drag down, and then so let's see if I can get it to 0.
This feels like one of those things where there's like a manual somewhere where it's like how to do SPH, and there's like a chapter that's like how not to do SPH.
Well, this is the challenge, right, of doing physical simulation. Is like, okay, sometimes you get some things that look like they could be physically plausible, and then other times not. I think this is working towards something better, right? Because kind of like we're expecting that repulsive force, and then as soon as they kind of get out, then they're kind of attracted back to the kind of like the way I would think a fluid might work. You know, as soon as the water, you know, wants to fill the space of the container. So as soon as it's not filling the space, it's trying to get out there. And then as soon as it's touching the walls, then it's going back.
It actually looks like the behavior I'd expect of a gravitic system that has no interacting particles. Like there's no like.
So let's turn the collisions back on and see.
Oh, okay. So far, so good.
What's that?
Like ripples before we were going out.
Yeah, I think so. So if we simulate, if we make the mass really, in other words, every particle is kind of interacting with every other particle, then let's see if we get any more emergent behavior. So this is actually cool. So actually, instead of 500 particles, let's drop that down back to 100 or so. And the reason why I'm going to do this is because I would expect we needed fewer, even less.
Some energy alien from some TV show.
So I guess now we could calculate, you know, if we increase density, so the object is getting harder, then if we increase density, we would expect the speed of sound to increase, right? And if we decrease Ks, we would expect the whole system to kind of speed of sound to.
The fact that the support radius determines like whether or not it'll spread out is kind of part of me is like that seems bad. Like, the support radiuses are like simplification factor. In fact, it's that powerful.
Yeah.
It's kind of like,
Another element too is that when you set the density and the Ks down to below 0, I feel like that also can have an effect. The heck is that guy doing? I think this is a good case of like our simulation like malfunctioning, right? That's one of those things you're like hoping that your numerical simulation doesn't explode and go crazy, right? Like it just did now. Okay, so that's interesting. Let's turn this down to smaller value. So obviously they're outside, you know, when they do get close, then they start interacting with each other. So you notice some of these pairs, when they start getting out, then I would expect, let's see if those two will start neat. Okay. So let's keep checking the let's keep going with the implementation, since it seems to be we got something happening here. So let's try to do the diffusion, right? So first we need to figure out kinematic viscosity, because we want to use real values. So let's see if there's any measurement. The Pascal second. In contrast with gases, there's no simple yet accurate picture for the molecular origins of viscosity in liquids. Now, some of this is dynamic, which I think is mu, and then there's the selected substances. Oh, list of viscosities. Let's check the table. There's this works. That's micropascals. Pure liquids. So mercury 1.5. I always like to pick things that might be something we would want to do. That's millipascals. Aqueous solutions, millipascals. Whole milk, ketchup. Oh, that gets really neat. Okay, I'm gonna look over here because I am curious if they mention the viscosity term. Is normally nu over rho. So the density of water is 1,000 kilograms per meters cubed. The kinematic viscosity of water is 1/1000th of its dynamic viscosity. Oh, okay. So if we take the dynamic viscosity and divide that by its density, then we can get K. So realistic values, what do you think are realistic values over here? So this is viscosity, 2.12 millipascals per second. I guess we got to look up the density of peanut butter. I wonder if somebody's the density of peanut butter.
Well, the question is chunky.
Yeah.
That's right. That might be 10 to the 6th versus 10 to the 4th. You know, it's a very dense peanut butter. Smooth style without this is kind of hilarious to me. Let's look over here.
Let's look at the chart.
The question of chunky versus smooth. Density equals weight divided by volume. We would like kilograms. Okay. Divided by, where is cubic meter? Okay. So we got 1082.
About water.
That's strange. I wasn't expecting that.
That sounds about right.
Peanut butter? As dense as water? I guess it's, if most things are made out of water, we shouldn't necessarily expect it to be different than water. Just maybe to some degree.
I mean, it does seem a little high, but...
No, I mean, you're thinking that it should be more packed in there, but I guess if there's more interaction with the whatever makes up peanut butter, then...
Well, I mean, just imagine a jar of peanut butter. Now imagine the exact same thing full of water. You imagine they weigh about the same.
Yeah, because a gallon of water is about 8 pounds. So I guess a gallon of peanut butter. Oh, yeah, let's look at that. 4, but we want pounds. 9 pounds. Okay, so that checks out. So it is. Density of peanut butter is approximately the same thing as water. These are the kinds of things, right? You know, you just think. Sometimes you think. Sometimes you just think density is like. Well, it's thick, right? So obviously it's more dense. You can pack more in there, but okay.
Viscosity is its own magical thing.
It's its own magical thing. Okay, so good to know.
I wonder how many foods or products aren't about as dense as water.
Yeah, probably like the hairy type ones.
Yeah.
Desserts, meringues, or whatever. Peanut butter, like all the What is this website?
Why? Why do they do it?
Because somebody has to.
Substances.
Probably all like
Okay.
I don't know. They have a section for passwords on this website. This is a very strange website. The more I look at their website, the more confused I am about what they do.
finance, food, health.
Gravel.
Coral
That means it's on
sand.
section.
I think it's really just for all these ads you see on this.
I'm thinking so. Density.
5.
Okay.
Nutritional values.
So density of sand, so a cubic meter over where's the kilogram? 2,000. So sand is about twice as dense as water. So I guess rocks, right? You know, that's okay.
They happen to have a gallon of it. Weighs 17.5 pounds.
That's right. Okay, so I guess when we're talking kinematic viscosity, then if it's whatever the rho, that's density. So millipascals seconds. Okay, so so whole milk has very low viscosity, whereas ketchup and honey have very high viscosities.
Ketchup's weird though because its viscosity is dependent on non-Newtonian factors. Yes, I know this.
Yes. And then peanut butter, 10 to the 4th, 10 to the 6th. Pitch is really,
Oh,
Do they have pitch in here?
You guys familiar with the pitch drop museum exhibit?
no.
Apparently, they made a museum exhibit, which is this container of pitch with a small hole in it, maybe a funnel, and it's super thick, and so it drops very slowly. The thing is apparently no one has ever been in the room when a drop has come out.
But drops have come out.
Yes, they've recorded it on camera, but it's so slow that it's like.
That's pretty great.
Okay, so I guess we divide this by, approximately 1,000. So we subtract 3 off those. So that value that we're expecting could go from basically 0 to, let's say, pitch. I think pitch is interesting because same thing with peanut butter. So we could simulate peanut butter, I guess, if we get the viscosity right. So we're looking at anywhere from numbers from basically 0.
0, 0, 2 to 10 to the 8.
So about 10 to the 8. Okay, so clearly we need to maybe we just need to make that the it's to the power. So if you have values of 1 to 8, then that's going to get you or 0 to 8, then that'll get you basically 1 through 10 million or whatever. So we have a lot of leeway with the diffusion. Okay, so diffusion over here is let's see here. So the only thing we haven't applied is diffusion, and according to the equations over here, the diffusion term is the current velocity, so j minus I over rho times the Laplacian of xi minus xj. Okay, so I have uj minus ui ddw, and let's see if that's so mass of j divided by the density for I times uj minus ui and ddw. So I think theoretically U grade should already be done. Well, let's just see what happens. So let forces equals the only thing we haven't added is a measurement for viscosity. So let's go ahead and let's add a parameter for that. So we're going to set drag back to 0 because I'm expecting that let's go with a value of 1, and we can expect values from 0 to 9 or 10. Let's go from there. Okay, this dot new equal and power of 10.0 to whatever that value is. We'll just set the initial value to 1.0. Okay, so now if we're calculating U gradient, then we need to multiply the kinesmatic, the viscosity times yeah, we can just do that right over here. Okay, so let's see what happens if we do this. It might be doing something. Well, let's turn the objects up.
What do we expect? What would be good?
Well, yeah, I would expect viscosity to like really slow it down. Like you were thinking, if we set it all the way high, it turns into sludge. Like, you know, but what's that? Should kill the velocity because
I guess velocity.
what's that?
You put the power in
Yeah, we're raising 10 to
when it gets to the range.
10 to this power, because if it's 10 to the 0, then we get 1. If it gets 10 to the 8, or then we get like a huge number. We're going to have to play with this some more to see.
So these ones on the outside are drops that got away.
Yeah, in a way, basically, they're drips. They're drips.
And if we add gravity, it'll kind of splash to the bottom or something.
Yeah. You want to? Should we add gravity?
I mean, would it be hard to do real quick? I'm just interested in what it would.
Just add gravity for external force. It's like
Could be it. It's just like, what did we say, honey? Or what did we say? Peanut butter? I mean, splashing.
Let's turn this up, see what happens. Okay, let's add our magic factor drag.
Yeah, I mean, it definitely looks like splashing. Right?
Okay, and let's add collisions.
Yeah, should do that.
There we go. Okay, so let's see what happens. Let's see if we've maybe been successful with our fluid simulation here.
Well, part of the reason it's bouncing so much isn't it the wall a reflective bounce? Like there's nothing to absorb the energy, so it's just all getting put back.
I think what we're doing is if we do hit a collision, then it. I can't remember if we're just flipping the sign of the velocity if it collides or not.
For the particle collisions, you just have it so that it pushes them outside of each other. I don't know about the walls.
Okay, so I'm gonna.
Can we implement more complex collisions?
I thought when we looked at like the last.
That's still not going to go up having viscosity to look.
Let me turn the drag down so we're not. There we go. Okay. I think we're technically done, so I'm going to turn off the streaming.